तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. This is the second lecture in the video course on electromagnetic fields aimed at EEE students. Last lecture I had introduced the course, discussed the syllabus, the textbook, and talked about some of the conceptual tools you will need. And then I had introduced the basic elements of vectors. So, this lecture I am going to continue that and take it to the point where we can use these, we can use vectors in our equations in electromagnetic theory. One of the most important things we have to do with vectors is to write them in coordinate systems. So, let us take a look at what that implies. I have a vector. Remember what I said last time, a vector is a direction along with a magnitude. So, this is any vector, let us say it is a force vector F. As I mentioned last time, if I draw a line underneath the symbol, it means it is a vector. Now, if I have 3-dimensional space, I can imagine drawing many different vectors in it. There can be vectors coming out of the board, there can be vectors going into the board, to the left and to the left and to the right. One of the standard results of vector spaces, which you would have learnt in your maths courses, is that for 3-dimensional space you can have only 3 independent vectors. An example is the unit vector along x, the unit vector along y, and the unit vector along z. And we know that any vector can be built out of these 3 vectors. For example, I can build a vector called 4 units along x plus 3 units along y plus 2 units along z. And any vector at all can be constructed using these 3 vectors. But there is no requirement that we should use these particular vectors. I could have used some other set of vectors. For example, supposing I defined vectors, a vector u which is nothing but unit vector along x, a vector v which is the sum of unit vectors x and y, and a vector w which is sum of unit vectors x and z. So, if I had to draw them, this is what it will look like. I have a coordinate system, this is x, this is y, this is z. My vector u is this. My vector v is actually this way, and my vector w, I have to draw a square this way, So, I have 3 vectors of this type. U is actually along x, V is in the x y plane, it is midway between x and y, and W is midway between x and z, it is in the x z plane. Now, it turns out that I can use u, v and w to construct any vectors I like. Just like I could construct using x, y and z, I can construct any vector at all using u, v and w. Let us try it out on this vector itself. I am going to call it z. How will I do it? Well, what I do is I try to figure out what these 3 vectors, unit vector along x, unit vector along y and unit vector along z, what these are in terms of u, v and w. So, what are they? Well, x is easy, x hat is nothing but u itself. I have got it there. But what about y hat? Y hat, well, y hat appears only in v. It is equal to v minus x hat from this equation. But x hat itself is u. I have already got that equation there. So, it is equal to v minus u. Similarly, z hat is equal to w minus x hat, which is equal to w minus u. It is a particularly simple example because I chose it that way. So, I can write down what x unit vector along x, unit vector along y and unit vector along z are in terms of u, v and w. So, then I will try to write what z is. Let me write what it was earlier. Z was 4 x hat plus 3 y hat plus 2 z hat. But I have expressions for what these are. So, it is 4 u plus 3 times v minus u plus 2 w minus u. All right. All I have done is I have taken these expressions and substituted for x hat, y hat and z hat. I can collect terms. I can collect terms because vector addition is associative and commutative. You can read all about that in the textbook. Those are just mathematical ideas which say that we can shuffle together any such expression. So, I am going to write it as 4u minus 3u minus 2u plus 3v plus 2w. So, I have taken the minus 3u, brought it here, the minus 2u and brought it here. What does that give us? It gives us that z is equal to minus u plus 3v plus 2w. It's a rather strange result. I have a nice straightforward vector. If I was plotting it, it's 4 units along x, it's 3 units along y, it's 2 units along z. So, I would just draw the rectangle, complete it, make a cube out of it, and this point, an arrow drawn from the origin to that point is my z. Now, for some strange reason that z actually says it requires minus u. To start with, we wanted 4 units of u, but once we have taken care of v and w, we want actually minus 1 unit of u. The reason why this strange result happens is because when we look at the elements we use to construct our z, u, v and w, what you find is that to construct w and v, you not only moved in the directions y and z, you also moved in the direction x. So, z actually has 4 units along x, 3 units along y and 2 units along z. To take care of the y and z, you have to move along v and w. But when you move along v and w, you end up moving along x as well. You move so much along x, you actually move 5 units along x. So, by the time you have taken care of this distance and this distance, you have already gone beyond in x. So, you needed to correct it by coming back. So, that is why you ended up with a minus u. But what this means is that if you had such a strange coordinate system like u, v, w, you could not predict ahead of time how much u, how much v and how much w there is in this vector z. A straightforward vector, but by the time you are finished with figuring out its coordinates, you are getting strange answers. So, this is why people have come up with some simpler coordinate systems, some useful coordinate systems which do not confuse us. These coordinate systems are called orthonormal coordinate systems. So, what is an orthonormal coordinate system? For any vector z, I can always write my minus u plus 3v plus 2w. Supposing I now want to take the dot product of this z along some direction. So, I say I want to know how much u there is. So, I do dot product z dot u. Well, z is already given to me. So, I can write minus u plus 3v plus 2w dot u. Now, this dot product is distributive. That means, if I have a sum of vectors dot u, that sum can be pulled out. So, it can be written as minus u dot u plus 3 v dot u plus 2 w dot u. And immediately there is a problem, because this v dot u and w dot u, what are they actually? V is unit vector along x plus unit vector along y dot unit vector along x. So, it is equal to 1. W dot u is unit vector along x plus unit vector along z dot x, which is also equal to 1. Which is why when you take z dot u and add it all up, you will get 4. minus 1 plus 3 plus 2 equals 4, which is not surprising at all, because we started with z equals 4 x hat plus 3 y hat plus 2 z hat. So, we had to get 4 out of it. But you can see that this is a very confusing situation. I want a simple dot product with this building block vector, and the answer does not turn out to be minus 1. Answer turns out to be something else. If the answer is to turn out to be minus 1, I would require this would be 0 and this would be 0. If they were both 0, then the answer would come out directly from here. Now, that happens in the case of Cartesian coordinate systems. Let us verify that. Take the same vector z, and I want to do z dot y hat. So, then I would say it is equal to 4 unit vector along x, 3 unit vector along y, 2 unit vector along z dot y hat, which will be equal to 4 x hat dot y hat plus 3 y hat dot y hat plus 2 z hat dot y hat. But here we know our coordinates. This is x, this is y, this is z. We know that if a vector is along x and a vector is along y, there is 90 degrees between them, x dot y is 0. If there is a vector along z and a vector along y, there is 90 degrees between them, y dot z is 0. So, this becomes 3 y dot y, and since the length of y is 1, y dot y also becomes 1, it is equal to 3. So, for the Cartesian coordinate system, if you take the dot product with one of the building block vectors, you get the coefficient that was used to build up your vector. It is a very useful property of a coordinate system, because that way you can figure out how to form this vector z given the building block vectors. All you have to do now is say that my vector z is equal to z dot x hat along x hat plus z dot y hat along y hat plus z dot along z. It is a different z from this, bad choice of notation. This is true in coordinate systems like the Cartesian system. It is not true in bad coordinate systems like the one I used, UVW. It is a major difference, and it is so major that nobody uses non-orthonormal coordinate systems if they can avoid it. So, what are the properties of an orthonormal coordinate system? We know that x hat dot x hat is equal to 1, x hat dot y hat equals 0, x hat dot z hat equals 0. Similarly, x hat dot y hat equals 0, y hat dot y hat equals 1, y hat dot z hat is equal to 0. Thirdly, we take x hat dot z hat, we get you should get a unit matrix. Okay. This was done upside down. This is the general property of an orthonormal system. So, if I have a system consisting of vectors EI and I want to say they are orthonormal, so I will go from some 1 to let us say n, then I will say that if I take any EI, dot it with any EJ, the answer will be 1 if I equals j. 1 equals I equals j, I equals j, I equals j, answer is 1. It is 0 if I not equal to j, and you can see off diagonal everything is 0. Let us look at some examples. What for orthonormal systems, they include all the common coordinate systems. Obviously, the Cartesian coordinate system. We have just seen that it is orthonormal. But here is another coordinate system that is orthonormal. This coordinate system looks like this. This is the x, y, z. The z hat is a unit vector along z. X hat plus y hat divided by root 2 is a unit distance along x and y. So, I go on the diagonal of the square formed by x and y, but I divide by root 2. I do not go the full distance. Then x hat minus y hat, I have to go backwards. I go on this diagonal, again I do not go the full distance, I go 70% of the distance. Now, I know that each of these angles is 45 degrees. So, obviously, this vector dot this vector is 0, and both of these are 90 degrees from the z vector. So, they are all orthogonal to each other. Let us just verify that. X hat plus y hat over root 2 dot x hat minus y hat over root 2 is equal to, well, there are 4 terms in this. X hat dot x hat, which is 1, x hat dot minus y hat 0, y hat dot x hat 0, y hat dot minus y hat minus 1 divided by 2 into 0. So, these are orthogonal. Are they orthonormal? Because I need also this condition, EI dot EI is equal to 1. So, if I just dot product this by itself, what do I get? X hat plus y hat over root 2 dot well, x hat dot x hat is 1, x hat dot y hat is 0, y hat dot x hat 0, and y hat dot y hat is 1 over square root of 2 multiplied by square root of 2. So, square root of 2 squared. Obviously, square root of 2 squared is nothing but 2, and the numerator is also 2. So, it is equal to 1. This is a general statement actually, if I take the x, y, z coordinate system and I rotate it any way I like, I can rotate it about the z axis, that is what I did here. I can rotate it in general in 3D, it will still be an orthonormal coordinate system. What about some other systems? Here is one that you should be familiar with. This is what is called the cylindrical coordinate system. So, this is a system where I have the z axis, but instead of x and y, I now choose to think in terms of circles. Any point I say has a radius r and an angle with the x axis theta. So, any point in 3-dimensional space can be captured by specifying r, theta and z. We know we can do that because x is equal to r cos theta and y is equal to r sin theta. So, if I can specify a point in x, y, z, I can specify it in r, theta, z. But what are these quantities? The unit vector along z is nothing but z hat. The unit vector along r means keep theta constant, keep z constant, change r. So, I am now going to draw a general point. We are on a cylinder. So, we have come to some height z and we have come to some angle theta. At this point, the z direction is vertically up. This is z hat. The r direction means keep that z fixed, keep that theta fixed, increase r. So, you go on that line. This is called the r direction. The theta direction means keep z fixed, keep r fixed, but vary theta. So, if you vary theta, you are moving along the circle and the direction along the circle is this. Now, once again r and theta unit vectors are clearly orthogonal to z, but what about between themselves? Well, if you look from above, it is a circle. This is the x axis and you are here somewhere. So, the r is along the radius, theta is along the tangent. So, one is tangential, the other is normal. It is easy to show these two are 90 degrees. So, this is again an orthonormal set, but it is a very strange orthonormal set, very useful, but very strange. It is strange because supposing I change my angle, I go to a point there. So, I have got a new theta now. My z hat has not changed, but my unit vector along r no longer points in this direction, it is pointing in that direction. And my unit vector along theta is now pointing this way. So, this is a coordinate system that depends on the point where you are looking. If you look at this point, r points this way. If you are looking at that point, r points there. If you look at this point, r will point away from the origin in that direction. But even so, this is an orthonormal coordinate system, which means that if you take these three, you will still get EI dot EJ is equal to 1 if I equals j, 0 if I not equal to j. Similar to cylindrical coordinates, there is a spherical coordinate system. I will introduce that later. It is introduced in the book and you can read it up, but there is no new concept there. It is the same idea that if you move along one of the coordinates keeping the other two fixed, you get a direction, and that direction defines a unit vector. Okay, now let us put the concepts we have got so far to work. Supposing I have coordinate system and let us say a satellite is following some trajectory. The satellite is experiencing gravity at all points of its orbit as it is falling towards Earth. I want to know how much kinetic energy does the satellite gain as it moves. Now I am going to take a simplest case. I should really be using a spherical coordinate system. I will pretend that the Earth is flat. So the satellite starts at a position R1, goes to a position R2, R3, R4 and finally say Rn. What do I mean by these R1, R2? I mean I can draw a line from origin to that point and its coordinates are R1. R2 would be a line joining the second point. R3 to the third, R4 to the fourth. So every point in space defines an arrow going from origin to that point that has a distance and it has a direction. So if I look at R1, it is really x1 so it is this distance x1, this distance is y1, this distance is z1. So it is x1 along x direction plus y1 along y direction plus z1 along z direction. Similarly, R2 is x2 along x direction, y2 along y direction plus z2 along z direction and so on. Now the distance between R1 and R2 is this vector. I will call that R12, and this vector which is the distance between R2 and R3 I will call R23. Distance between R3 and R4 I call R34. From my vector addition I know that R1 plus R12 is equal to R2, because if I go to R1 then go further by an amount R2, I reach a point which is nothing but R2. So this is vector addition. Similarly, I can write R2 plus R23 equals R3. That is, I go to R2, then go a distance along direction R23, I will reach R3. And similarly, R3 plus R34 equals R4, and so on. Supposing I want to write R4 in terms of R1, what do I do? Well, I will write R4 is equal to R3 plus R34. But R3 itself can be written, it's equal to R2 plus R23 plus R34. But I can substitute for R2. So when I do that, I get R4 is equal to R3 plus R34, R2 plus R23 plus R34, R1 plus R12 plus R23 plus R34. I have put brackets because that is how I have defined these quantities. But this is where some rules about vector addition come in. The brackets do not matter. So I can as well write this as R1 plus R12 plus R23 plus R34. So what it means is, to get to R4, I could have gone to R3 and gone to R4, but I could equally well have gone to R1, gone R12, gone R23, gone R34. It's the same thing. It's obvious that it's the same thing, but mathematically what it means is these brackets can be dispensed with when we do vector addition. What is the use? Well, we would like to know how much kinetic energy changed. Change in kinetic energy is equal to work done on satellite. Well, there is a force due to gravity, and the work done is force dot distance travelled. Well, what is the distance travelled? Well, it is R12 plus R23 plus R34, because if I took R4 minus R1, this is all that remains. Now I decompose this R12, R23, R34 into components, and what do I get? I get the force due to gravity is minus mg along the z axis, it is pointed downwards, dot R12 in the x direction x hat plus R12 in the y direction y hat plus R12 in the z direction z hat plus etc. Large number of components. But now I know x dot z is 0, y dot z is 0, and only z dot z remains, and z dot z is 1. So I need only to keep the z components. So what I get is that the change in kinetic energy is equal to minus mg times r12z plus r23z plus r34z plus r n minus 1 n along z. Now, each of these, if you look at this, is just the amount of distance by which the trajectory dropped in z. So, it can be written as minus mg z2 minus z1 plus z3 minus z2, many other terms, plus zn minus zn minus 1. And you can see that the z2 will cancel out and the z3 will cancel out, and so on and so forth. So, you are left with minus mg into zn minus z1, which tells us what we already knew, which is that when an object falls some distance, the gain in kinetic energy is nothing but the mg times the distance it falls. So, it is not as if vector algebra gives you anything new. That is not the purpose. The purpose here is to show that something familiar that we already know is consistent with whatever vector algebra is saying. Okay. Now, we have about 15 minutes more. Let us go to another topic which I introduced last time, which is the curl, sorry, the cross product. So, up to now we have talked about coordinate systems and dot product, but there is an equally important operator called the cross product. And as I told you last time, the definition of cross product is that if you have two vectors, say f and g, and if they point, if they have an angle theta between them, then f cross g points in a direction that is 90 degrees to both vectors in a direction which you will get by using a right hand rule, that is, if you take a screwdriver and screw it in so that f comes into g, the direction in which the screwdriver will move, that direction is the cross product direction. So, this would be f cross g. What is the magnitude? This distance is going to be equal to magnitude of f times magnitude of g times sine of the angle between them. What this sine theta means is that if f and g point along the same direction, theta would be 0 and sine theta would go to 0. So, you will not have any cross product if two vectors are pointing in the same direction. On the other hand, if two vectors are pointing exactly 90 degrees apart, you get maximum cross product. This is exactly opposite to dot product. Dot product, if two vectors are pointing in the same direction, you get maximum. If two vectors are pointing at 90 degrees, you get 0. Now, supposing I take these two vectors f and I say that this is f x x hat plus f y y hat plus f z z hat, and I say g is g x x hat, g y y hat gz z hat. Now, it's not totally obvious that what we are going to do is going to work, but I think it should be taken on faith at this point. This definition of cross product is actually what's called a bilinear operation. It is linear in each of the two vectors. So the result is, when you write f cross g, it is actually equal to the representation of each of these, fx x hat, fy y hat, fz z hat cross gx x hat, gy y hat, gz z hat. But this cross product defined this way, it is not at all clear that this is correct, but it is, actually distributes over the multiplication. So you get fx gx times unit vector along x cross unit vector along x plus fx gy unit vector along x cross unit vector along y plus fx gz unit vector along x cross z hat. Similarly, fy gx plus fy gy plus fy gz plus fz gx As I said, this is not obvious, but it turns out that the definition does in fact distribute. Now, if it is true, then there are certain things you can immediately see. X hat cross x hat is 0, y hat cross y hat is 0, z hat cross z hat is 0, because a vector pointing on the same direction as another vector cannot have a cross product. Now, what about x hat cross y hat? Well, let us draw the coordinate system. If I use my right hand rule and try to turn a screwdriver from x to y, well, I point along z. So I have x hat cross y hat equals z hat. Similarly, if I do y hat cross x hat, I point in the opposite direction. If you do x hat cross z hat, you will see that and similarly, if you do y hat cross z hat, you get plus x hat, and z hat cross y hat gives you minus x hat. So let us write out these terms. When you write out these terms, what you get is f cross g is equal to minus fx gz along the y hat direction. I am sorry, I started with the wrong term. Fx gx goes away, fx gy along z minus fx gz along the y hat direction, then fy gx, y cross x is minus z along the z direction, fy gy, there is no cross product, fy gz y cross z is x, fz gx, z cross x is y, fz gy, z cross y is minus x. And fz gz will go to 0. So, we have at least come down to 6 terms. Now, you can collect terms according to each unit vector. So, what does this become? It becomes x hat times fy gz minus fz gy plus y hat times, there are 2 terms, fz gx minus fx gz plus the z term, which is fx gy minus fy gx. Now, all this algebra was in order to get this expression, because when we look at this expression we recognize it immediately. This is nothing but the determinant. So, you can write the determinant form of cross product. You can say f cross g is equal to the determinant x hat, y hat, z hat, fx, fy, fz, gx, gy, gz. Because when you take the determinant, you choose any row. Let us say we chose the top row. Then we take sum over all the minors. So, x hat times determinant of this minor, which is fy gz minus fz gy, plus y hat times this minor, which is fz gx minus gz fx, plus z times this minor, which is fx gy minus fy gx. So, you can see that the cross product is intrinsically dealing with a determinant of these 2 vectors. Now, why is that important? Well, one of the important applications that immediately comes is that if I wanted to take the cross product and dot product it with something else. So, supposing I said f cross g dot h. So, what would happen? I would take this expression and I would say that this is equal to the x component of h times f cross g x component plus hy times f cross g y plus hz times f cross g z. But f cross g x is nothing but this piece. So, if I simply replaced this determinant and put in hx, hy and hz, I would be getting h dot f cross g. We will come back to this later, but this is an extremely important concept because it talks about volume, and it is very important when we, if we get to it in this course, but it is very important in general when you want to find the volume of different enclosed by different surfaces, because these vectors in general will not be 90 degrees. So, they will point in various different directions, and you can draw a three-dimensional structure using these three vectors. And what this tells you is nothing more than the volume of this parallelepiped. With this, I am completing the review of vectors that I had planned to do for this course. You are already supposed to know all of this. So, this is more review so that in case you forgot any of it, you will get reminded of it here. If you are not comfortable with any of these concepts, please do go back to your previous mathematics book and review it. Thank you.